Hi guys, we're going to talk about Newton's second law today. So you should have just finished up a lab and you should have come up with a couple different, seen a couple different relationships. So just to briefly go over Newton's second law, the idea is as force increases, the acceleration should also increase. So we should see an increase in the acceleration. This is a direct relationship. And this is when mass is constant. Also, you should have seen as mass increases, our acceleration should have decreased. This is an inverse relationship. And this was when force was constant. So that's the basics of Newton's second law and like really what we're getting down to. Newton's second law is this equation that's on your formula sheet, that acceleration equals net force divided by mass. Now, something we really need to note when we're talking about net force divided by mass is, I just want to remind you, net force is the sum of all your forces in like a particular direction. So specifically, I'm talking about here in the direction of motion. And I mean like the X or Y direction. I don't mean like I'm moving to the right, so I'm only looking at the net forces to the right. I'm meaning like I'm looking at all of the forces in the X direction or all of the forces in the Y direction. There's some steps that we want to take when problem solving and figuring out Newton's second law problems. So we want to establish a system. Really, that means when I draw my dot for my force diagram, what does that dot represent? Does the dot represent the two boxes put together? Does it represent, a bucket and a rope? What does the dot really represent? So in this first situation, it says I lift a 30-kilogram object with a force of 400 newtons. Well, that dot, my system would represent that object. Then you want to draw your free body diagram. So I'm going to do that for this first problem right here. So I already said that my dot is going to represent my object, and I'm going to draw a free body diagram. I'm going to draw right here. So here, draw the free body diagram. I've got an object that's being lifted, but there's always force gravity. So force gravity, and then I have an applied force up. That's all it is for that. So drew my force diagram. Then I need to determine what direction is positive. I'm going to make up be positive. I pretty much always make up positive, down negative. I don't really find a reason to mix it up and flip it around. I feel like it's just a place for you to kind of get confused. Then we want to find the individual forces and vector components. So it already told me that I lifted this with 400 newtons, so 400 newtons up. And then we need to determine what's the value of our force gravity. Now remember, force gravity is mass times gravitational field strength. So force gravity is going to be 30 times 9.8 newtons per kilogram, which gives me a force gravity of 294 newtons. It's a bad 4. Let me rewrite that 4. There we go. So now really what the problem's asking me, so we're going to go to our next step. We found our individual forces. Now we want to find our net forces. So we're going to add all of our forces in the same direction and subtract all of them in the other direction. So these two are opposite directions of each other. So net force is going to equal my applied force minus force gravity. So when I want to actually calculate what my net force is, that's 400 minus 294. So my net force is going to equal 106 newtons. So I'm going to erase this work down here real quick because I'm going to run out of space. So last step, then we want to solve for whatever we're solving for. We wanted acceleration in this situation. So we know acceleration is the net force divided by mass, which gives me 106 newtons divided by my mass, which was 30 kilograms. So my acceleration is 3.53 meters per second squared. I'll highlight that answer. Not so bad. All right, let's look at the second problem of this type. And we're going to get a little trickier. So you put a 9-kilogram box on a small scale, then you push down on top of the box with a certain amount of force. If the scale reads 137 newtons, how much force did you use? So let's draw a picture. So I'm going to have this dot represent the box. And we know there's force gravity acting on the box because it's always there. I also know that I pushed down on the box with some sort of applied force. And I put those arrows both coming from the dot and not stacked on top of each other because the forces are both being applied to the dot. Then I've got a force normal. Now this force normal is larger because it's going to have to be, if my box isn't accelerating, the force normal is going to be the same size as if these two were stacked together. So that's why that force normal is so large. It gives me some information. It told me my scale read 137 newtons. And we know that force gravity is mass times gravitational field strength. So I can do 9 times 9.8, which gives me 88.2. So really, I just want to solve for what this applied force would be. So our net force, since our object is not moving, we can solve for net force, which is going to be equal to 0. But that's really going to be my force normal minus my force gravity minus my applied force. So I can plug some numbers in. 0 equals force normal, which was 1 second, I deployed a keyboard on my end. 137 newtons minus my 88.2 newtons minus my applied force. So really, to solve for applied force, I just need to solve for all of this. So this, when it's all said and done, this gives me 0 equals 48.8 minus F applied. So if we want to solve for what our applied force is, and I'm running out of room, so I'm just going to erase that last row I just wrote. If I want to do some algebra and figure out what my applied force is, that gives me applied force equals 48.8 newtons. Alrighty, so really what we're doing here is we're taking this idea of force diagrams, Newton's first law: if an object is in motion, it stays at motion; if an object is at rest, it stays at rest, and now applying it to some numbers using Newton's second law. All right, next one. A 2-kilogram object is moving horizontally with a speed of 4 meters per second. How much net force is required to keep the object moving at the same speed? And in the direction if it's a frictionless environment. So let's think about this. If I've got an object, it's got force gravity, it's moving across a surface already, and we already have a velocity going this way. If we want to keep that object moving at the same rate, I actually don't want to apply a force. I want my net force to be equal to 0. Well, horizontally, if it's a frictionless environment, that means there's no friction right here. There's no force being applied right here. So to keep this object moving at a constant speed, we need to keep this net force of 0. So how much net force is required? 0 net force, because there's no friction. Someone's kind of like a sneaky, tricky kind of question there. All right, I've got a couple more examples where we're going to kind of dig into the more nitty-gritty side of this now. So our first example we're going to look at is Earth is exerting approximately 100 newtons of force on a 10-kilogram suitcase. This is when you're using like 10 meters per second squared, or 10, it's newtons per kilogram when we're talking gravitational field strength. But it's when they're saying, so here they're really just saying if G is equal to 10. Suppose you exert an upward 120 Newton force, I'm going to underline my numbers here, on the suitcase. If the suitcase starts at rest, how fast is it traveling after it lifting it for 0.5 seconds? So we're going to follow these same steps we just talked about. I'm going to start by drawing a force diagram. So the dot represents my suitcase. We've got force gravity and force applied. So let's write out a list of things that I know. I know my mass is 10 kilograms. I know that, actually, I'm going to erase and give myself some more room here. So I've got a mass of 10 kilograms. We know that the Earth exerts a force of 100 newtons downward on this. And we also know that I applied a 120 Newton force upward. So if we want to start, because our end goal is how fast something is, and we don't really have enough information. If I were to break this into parts, we've got VI as 0 on this side. We've got time is 0.5 seconds, but we don't really know anything else. We want velocity final. So just thinking through most of their kinematic problems, we always want to use something with kinematics that's going to give us, we need acceleration for this. And I can use forces to solve for that acceleration. So I can say my net force, and I'm going to write net force like this, equals my mass times acceleration. But more so, it's going to be my force applied minus my force gravity. So my net force is going to be equal to 120 minus 100, which gives me a net force of 20 newtons. So when I think about that Newton's second law equation, acceleration equals net force divided by mass, I can take my 20 newtons divided by my 10 kilograms, and that's going to give me 2, and technically the unit's newtons per kilogram, but that's the same thing as meters per second squared. So when I go to calculate my velocity, now I have this 2 meters per second squared over here. So we have velocity initial given to us. We have time and acceleration, so we can use the first kinematic equation to solve for velocity final. VF equals VI plus acceleration times time. So velocity final equals 0, and I'm going to be bad and not put my units in, times 2 plus 2 meters per second squared times 0. I ran out of room, so I'm going to go and get rid of those units. Times 0.5. So really my velocity final here is going to be equal to 1 meter per second. This is why it's so important to know how to do those kinematic problems, because I have to use forces, but then to get my real answer, I have to use that kinematics equations. That's why we're lumping these two units together. All right, let's look at our next problem. This next one, Michael Holmes, he's 70 kilograms. I'm going to underline my numbers that I have. Was moving downward at 36 meters per second. Now it's downward, so that's really going to be negative 36 when we do this. And was stopped by a 2-meter high shrubbery and the ground. Estimate his average force exerted by the shrubbery and the ground on his body while stopping his fall. So let's draw a picture to help us out. We've got force gravity, and we've got force applied. We can do a couple quick calculations to solve for the individual forces. Force gravity is m times g, which gives me 70 times 9.8, which gives me a value of 686 newtons. So that's the force gravity. Now our end goal that we really want is what's this applied force? That's our end goal of this whole problem. So we need to do some calculations then to help us get there. So we're going to list out what we know. I know the velocity initial while he's falling is 36 meters per second. That's going to be mainly for like before he like hits the brush, yeah. We also know that he was slowed down over a change in position of 2 meters. Now that's going to be, he's moving in the negative direction. So there's some things we need to point out. That's a negative 36, and it's a negative 2 here. So then we know his velocity final is going to be equal to 0 meters per second because we're stopping him, and we want the acceleration because acceleration is our way to kind of transfer back and forth between kinematics motion talk in forces talk. So thinking about this, I can actually go and solve for his acceleration because I have VI, VF, and delta y. Because we have this third kinematic equation, VF equals VI squared, VF squared equals VI squared plus 2 times A times delta. And I'm calling it Y because we're moving in the Y direction. So I'm going to plug in some stuff. I'm not putting my units in because I'm going to run out of space. 0 equals negative 36, and that whole thing's going to be squared, plus 2 times A times negative 2. So 36 squared gives me 1,296. So 0 equals, and I'm going to keep this negative 1,296 minus 4a. And I kept this negative, I kept this one negative, even though I know squaring it's going to make it positive, because it is still the negative direction. My object's moving in the negative direction. To solve for a, I'm going to move this to the other side, which gives me an acceleration of 324 meters per second squared, which makes sense. If my guy is moving in the negative direction, if he's going to slow down, the acceleration has to be in the positive direction. So that number checks out. If you were to get a negative number, that's probably because we assumed that this was going to stay negative here. But if you had a positive number here, it's really just good for us to know which direction the acceleration is going to go. So for the rest of this problem, now we just need to really figure out what our applied force is. So we have our net force equals the applied force minus force gravity. Now net force, we can substitute this in for as mass times acceleration, which gives me mass times acceleration equals my applied force minus force gravity. So I'm just going to plug in what I know. My mass is 70, my acceleration is 324. Applied force is what I'm solving for, minus my force gravity, which we found was 686. I'm running out of room, so it's going to get a little cramped here. So when this is all said and done, I get 70 times 324. I'm going to move this 686 to the other side, give me my applied force, which means F applied is going to be 23,366 newtons. Not a fun fall is the answer. Color that in. Which you can hardly see here. I don't know why this is frozen. It froze. 1 second. Oh, there we go. Okay, not frozen anymore. Hope you caught all of that in between. All right, now we're going to talk about elevators. Elevators, it's using the same skills, so don't be overwhelmed with an elevator. AP loves to ask questions about elevators. They really just love it. I don't know their fascination with it. But it's the same situation we've been talking about. So imagine, I'm going to draw a picture this time even. We've got an elevator, my lovely elevator, and there's a rope. It's a little abstract. There we go. So we've got an elevator, and the mass is 1,600 newtons. I mean kilograms this time. They're not giving me my mass in newtons. If they gave it to you in newtons, it just means the weight. And we know that it is moving downward at a speed of 12 meters per second. Over a distance of 42 meters, it's going to come to a full stop. So really, if we're going to make a list of these knowns that we have, I'm going to underline what we have. We have VI is equal to 12, but it's moving downward, so it's really negative 12. We know that we have a delta Y of negative 42 because it's moving downward. We have a VF of 0 because it's going to stop. And we're going to need some sort of acceleration. Now what we want to know what the tension force of the elevator is during this acceleration time period. So if I want to think about this, I've got force gravity, we're starting our steps, and force tension. We basically want to figure out what force tension is. Force gravity is going to be our mass times our gravitational field strength, which is 1600 times 9.8, which gives me a FG of 15,680 newtons. And FT is what we're solving for. It's kind of very, very, very similar to this last problem we just had, except it's the elevator context. And I have a graphic below this to help you out. So I want to start by solving for what my acceleration would be. We just did that. VF squared equals VI squared plus 2A delta Y. This gives me 0 squared equals 12 squared. I'm being bad not putting my units in. Plus 2 times A times 42. So this gives me 0 equals 144 plus, but we're going negative, so it's negative, and that should be negative. We need to throw those negatives in there. 84A. When this is all said and done, our acceleration is going to be 1.71 meters per second squared. I'm jumping through this kinematics part because we've done kinematics. It's not a new subject for us. So if I want to go and solve for what my force tension would be, I'm going to sum my forces. The sum of my forces equals, and I'm just going to jump in to put the mass times acceleration. You're going to see me start doing this, which is force tension minus force gravity. All right, mass, which was 1600, times the acceleration, which we got is 1.71, equals my force tension minus my force gravity, which is 15,680 newtons. So when we go and calculate this, force tension is going to be 18,416 newtons. Now I want to actually discuss this number real quick with you guys. This isn't like some important number in physics, but I want to compare this force gravity to this force tension because the upward force is greater than the downward force. So if I were to draw this, this arrow up here would have to be much longer than my bottom arrow. I want to make sure that I knew that because this force tension, let's say instead of us looking at the elevator as a whole, we looked at a person standing inside the elevator. So let's say we've got a person standing inside the elevator. Technically, your weight changes when you're on the elevator. If you're accelerating upward, accelerating downward, or if you're just normal. Now, if we've got a normal situation, you are your force diagram, and we have no acceleration, your force gravity is going to be equal to your force normal. However, if I have an upward acceleration, so my object is moving upward and we have an upward acceleration, or my object's moving downward and I have a upward acceleration, so I'm slowing down, we're going to have our force gravity is going to be less than our force normal. So tomorrow we're going to talk about this in class, but this is a situation where if you were standing on a scale in an elevator, your scale would read more than what your actual weight is. Now we kind of have the same thing where we can look at, you can have less than normal weight. So this is if you have a downward acceleration of any sort. So your downward force is more. So this would be a situation where your force gravity would read more because the acceleration is going in that direction. And your scale would technically read less than your normal weight because the acceleration is downward. And then finally, if this elevator cord were to break, we just have force gravity. And you would be in what we call free fall. These are some very specific things. We're going to talk about this tomorrow in class, but I wanted to introduce the topic before I had you guys dive into an activity.